Hello everyone, and welcome to the NEx Webinar series. This is our July webinar, and we are conducting webinars every month, so please stay connected for our upcoming sessions. I am Aparna Deshmukh, Technical Director with NEx, and I will be your moderator for today's session. We are excited to dive into our today's webinar titled, How Can Civil Engineering Education Embrace Non-Metallic Materials? ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for 1 learning units. So let's get started with a short description of our today's webinar. This webinar will discuss the current state of civil engineering education, the impact of codes on material usage, and present a vision for an innovative future incorporating non-metallic materials. It will also highlight the challenges of including non-metallic materials in the curriculum, given a limited space and a fixed structure, and explore creative approaches to introduce them into the education system. Our learning objectives for this webinar are as shown on the screen. Let's welcome and introduce our today's speaker, Dr. David Lang. Dr. Lang is an emeritus professor in the Department of Civil and Environmental Engineering at University of Illinois at Urbana-Champaign. He has over 30 years of research and teaching experience in construction materials. In 1997, he held the esteemed position of being the inaugural chairperson of ACI Committee 236, Material Science of Concrete. Throughout his distinguished career, Dr. Lang has been recognized for his outstanding research contributions. He was honored with the ACI Wasson Medal for Most Meritorious Paper in 2003, 2018, and 2020. He served as a president of the American Concrete Institute for the year 2018-19, demonstrating his commitment to fostering growth and excellence in the concrete industry. Let's welcome Dr. Lang and listen to his presentation.
All right. Good afternoon, everybody. It's a pleasure to be here. Thank you, Aparna, for the invitation to be part of your monthly webinar series. This topic is a really good topic that represents one of the most exciting, fast-moving areas of our concrete field. And so I've been involved in this things related to non-metallics for at least, I don't know, 3-4 years here, especially. And it is amazing how much is changing and how many new resources are being made available. So what we're going to do here today is talk about what are the next steps that need to be taken to help embrace this new emerging area of concrete technology into our routine engineering design function in the engineering side of things. And part of that is overcoming the barriers that we see to education, higher education. And that's what we're going to talk about today. So I wanted to first start with this idea of the emerging needs. The need for non-metallic materials is very strong, and there's a broad consensus that these kind of materials play an important special role in constructed facilities. Particularly their strongest advantage that is always referenced, it's not the only advantage, but the one that gets mentioned most is the fact that they have durability, they're non-corroding reinforcement. So especially in the kind of applications that you see on the screen right now, non-metallics represent an important advantage to the design engineer. And as engineers, we're always looking for the success of our projects. We don't need to line up with specific kind of materials for reinforcing other than for their success at serving the goals of the project. And so you can see that these are special projects that have corrosion issues routinely. My active participation came back in 2018. I was serving as president, and there became an opportunity to be part of a House subcommittee hearing on how can we overcome barriers to the use of composite materials in infrastructure. And so it was interesting for me to hear from others in industry how rebar, the GFRP rebar was being developed, and these extruded shapes were available in the marketplace, and no one was using them, or very few people were using them. And so you can imagine the frustration of people who are advocating for the use of nonmetallics, that what are we supposed to do to get through to the industry and make these really viable alternatives for reinforcing and reinforced concrete? And so we honed in on a couple different things, but mostly I think it had to do with the lack of standards and codes and standards. There's a quote here: adoption of advanced composite materials has been slow, due in part to the presence of two dominant design paradigms in commercial construction. So as I was preparing my remarks here, I see, look at what we do in civil engineering education. We have reinforced concrete 1 and 2. We have structural steel 1 and 2. That's what the civil engineers are trained to look at. They don't normally see non-metallics or composite materials as an alternative in these. And even if you go into the reinforced concrete textbooks, you don't see mention of polymeric materials, of non-metallic materials. Yet they are existing. They are emerging in the marketplace. So there will be numerous benefits if we can integrate these newer materials. And as engineers, we should always be in favor of supporting innovation, finding new and better ways to do a job, and so forth. But we need to support it with education, curriculum and so forth. All right, so this was one of the first times I slowed down to think about this problem, and it was an impactful experience for me. But it leads to these bigger questions. Why do we teach the topics we do in civil engineering? How is it that these topics get embedded in our body of knowledge that we see in almost every civil engineering program in the nation? And then the second thing is, why can I go back 30 years and find exactly the same curriculum as we have today? The same courses, the same, it's all broken up the same. And so why does it seem that we have so little change over decades of time? And that puts this onus on the professional educators that, are we resistant to change? What is that about? We don't normally think we're stodgy, but we sure seem stodgy. So we can think of some reasons that might be. And here are some things. Civil engineering is thought of as a conservative discipline. We are traditional. We favor popular means and methods. We favor proven solutions. We insist on safety. That is often brought out as a kind of a main explanation of why we are the way we are. Listen, our society depends on us for life safety issues. We don't want to play around with and be careless with adopting just any old new materials and techniques. And then the last one is, we tend to teach what we know. And that I think just about every professor will find some resonance with that idea. Oftentimes, we're even referring back to our old textbooks and our old notes to try to ground ourselves in the kind of messages that we want to pass on to the current students. So conservatism is not a bad thing, but it can be a barrier if it stops us from being innovative and allowing new and good techniques to rise to the top. So we look back, of course, almost every civil engineer has some kind of a mention in freshman year about the old Roman structures and how they've lasted so long, arches and masonry structures. And aren't these amazing? And they are amazing. But were the Romans great builders or great engineers? I'm not sure why we go back to these Roman structures that vigorously, when in fact they are not really that strongly engineered structure. The detail I'm picking on here is the engineering part. What does it mean to do engineering design? Were the Romans even doing engineering design? They really were not. I would contend they were not, because they didn't even have the tools, the mathematical tools, to describe the essential parts of design. Design requires an understanding of the mechanics. We need to know how loads can be applied to a structure, how those loads create stress through a material, and how that stress affects things like deformation and deflection. Solid mechanics really came along in 1600, 1700. I always like to get students to realize the real importance of Robert Hooke's, the Hooke's law, where we have linear elasticity described in the chart. And we always teach this as part with a spring and a mass and stretching and so forth, and this linear relationship between the mass and the displacement. But that basic law is so critical to civil engineered structures. It basically underlies everything we do in the 318 code. All the issues regarding to how to resolve the load carrying of these members, where we place the steel in the cross section, how big the cross section is. These are all derived from Hooke's law about linear elasticity. And so we have a lot to thank Robert Hooke for, Isaac Newton, other giants along the way. But today, of course, we're implementing these at even more of a sophisticated level with computers and so on. But so could we do real engineering before 1700? I'm going to say no. The Romans were builders. They were not engineers. But we want to think about how that developed after 1700. So this word, civil engineering, has the two words, civil and engineering. Why civil? Well, this was a period of time where late 1800s, it was a distinction from military engineering. So the job of the academy was now focused on municipalities, cities, developing structures for the public. And that became the term that stuck, civil engineering. And engineering, the argument I just made, that we're now going to have real calculation, real understanding of stress and strain. So we want to skip a couple thousand years past the Romans and move into the 1800s, late 1800s. And that brings us to this development of a new profession. And I will say that steel structures really led the way for reinforced concrete. And it's not a surprise. Steel behaves really good, very predictable, linear elastic behavior up to a yield point, but the yield point is not something that we need to worry too much about in normal serviceability. Our maximum loads, service loads are not in the yielding component of the stress strain curve. And so we see these examples, early examples. The Iron Bridge over this river in the UK, 1779. Eiffel Tower, 1889. This notable home insurance building in 1885 in Chicago. All these late 1800 buildings, and that leads us to this particular reference point. The Ingalls building is known as the first reinforced concrete building, and it was in Cincinnati. And there were quickly many other examples, particularly active industry in Chicago. All right, now imagine yourself back in 1900. Everybody's got this idea about how to do reinforced concrete, using concrete as a matrix, having steel running through it in different locations. And we're all in the business of making bridges and tall buildings. And there are arguments. People are doing it different ways. There's no standardization. And some notable failures occur. And now people are concerned about this is a threat to our young industry that focuses on reinforced concrete. How can we move ahead if the public doesn't trust our buildings to be safe? So this is how ACI was born. Around 1900, many people in the profession start to get together and realize that we need to have some kind of a partnership so we can standardize how to make, how to design with reinforced concrete. Now, diversion here for a moment, because we can go back a few years and we want to pick up this idea of how we are educating the new nation. And I especially like to reference the Morrill Land Grant Act, 1862. This was an important act of Congress. Each state of the union would get proceeds from the sale of federal land that could be used to establish a university. So every state went off to grab some of these resources. All they needed to do was find out where to put their university. And so Illinois put it in Champaign-Urbana, and all the other ones came along too. I don't know, I'm not going to list them all, but they were all about the same period of time. And you can see how the growth of these large universities has been amazing. University of Illinois was only 1,000 people back at the turn of the century, and now today it's 50,000 students. Our Granger College of Engineering is today maybe 15,000 people. So the point being that this has served an important role of preparing people for the profession and taking seriously this idea of addressing technology and preparing, great engineers, among other subjects. I had this in my slides, so I thought I'd show this too. The point I wanted to make here is look at all the founding dates. They're all within a couple of years because they're all being born out of this Morrill Land Grant Act. So everybody's making their own copy, and maybe it's been good to have this little competition among the big, and these are just Big Ten schools. So there's 360 colleges and universities that offer civil engineering courses. I think in ABET accreditation, there's something like 240 or so different ABET accredited departments. And so the university grew, as I've made the point. And as you know, Abraham Lincoln once famously said, yes, it would be nice to create a nation of great universities, but it will be absolutely awesome to create a nation of great football teams. Of course, that's not a possible quote because football wasn't played till 1869. And if basketball had been invented by the time, we remarked about that too. Okay, so back to the story. ACI was founded in 1904 to address the profession's needs. And primarily they were thinking about standardization and codes. Look at these dates, 1904, first code, 1910. Oh my gosh, we need to take find inspiration in that turnaround. 14 pages long, we need to find inspiration in that remark. So this was the first thing that ACI did, was try to put some rules together about how to do reinforced concrete. But in addition to the standardization and the codes, it was a gathering place for the profession and has continued to serve that main role ever since. I think most of the people on the webinar today are probably members of ACI, and I certainly have over my whole career really enjoyed it. It's my most important organization to participate in. And committees. Oh, we love committees at ACI. We have over 100 of them, and 100 technical committees. And Committee 318 made its first building code in 1941. So the code before that was a product of the Institute at large, but the Committee 318 started adopting and caretaking of the building code in 1941. And it's grown since then. Okay, so civil engineering, gatekeepers of structural design, that we certainly take seriously at ACI, that we know that our reinforced concrete structures are essential for the safety and functioning of a safe and prosperous economy. And I'm sure the people over on the steel structure side feel the same way. So these two main organizations, ACI and the American Institute of Steel Construction, are special because they are caretakers of code. ACI concrete code and AISC steel code. And that has been really important to see how we've developed civil engineering education. These two organizations, venerable organizations dating back 100 years, have been caretaking the code for decades. And we have seen textbooks prepared for reinforced concrete and for steel structures. And we've seen this embedded into the civil engineering curriculum as course titles, reinforced concrete 1 and 2, and so forth. And now along comes 2023, and non-metallics are trying to find their spot in this picture. How come we don't get our own course on non-metallic structures, non-metallic materials for buildings? What is the right vision of how we get into the curriculum? And that's where this talk is going to end up in the conclusions. Okay, so we need design codes clearly, and those are the first two I've mentioned. And now we have, we've actually seen the building code for structures made with non-metallics emerge in just the last couple of years. So we now have ACI 440 developing new code. And so this is one of the most important functions of ACI and NEx to drive these kind of things, bring the community together and encourage the development of effective codes and specs and guides. And 440 has done a great job of doing this, and others. So they're not the only committee that's working on such things. Okay, I might mention a couple other materials. Wood and masonry have their own organizations. In some ways, you know, we should sympathize a little with those guys over on the wood and the masonry side, because these guys feel, I'm sure sometimes, like they're the poorest stepsister or something to the big concrete and steel communities. Most departments don't offer design courses for wood and masonry. The bigger schools do, but many times those courses are reserved for graduate level, for structural engineers that need all the specialty working with different kind of codes, because these codes are different. They're unique, and so we want to address all the unique aspects of these codes and not assume that everybody's getting it on their first pass through structural engineering. Okay, so I've made kind of this point that the design courses in civil engineering exists only where code exists. Okay, what are the weaknesses of this traditional approach? The inertia of traditional design solutions tend to impede innovation. I would say very quickly that engineers ought not to feel that they need to be an advocate for a given material system. Engineers should serve the project, not the supply chain. We should be able to select from the full set of material choices. I don't think too many people argue with this basic idea that engineers, to be good engineers, you need to rise above the material competition issues. We want to pick the best material for the job. And when we get new technology like non-metallics, we might think of this technology adoption cycle. Where are we in the innovators all the way through where the majority of the field is using a new technology? We're definitely down here in the early adopters. We're beyond the innovators. We already have a community of committees that address code. We're in early adoption, and I see that there'll be some strides taken where the new engineers will learn about this even in college and bring this knowledge into their professional practice. I wanted to mention accreditation, because this is all the most of the engineers, by virtue of being a professional engineer licensed by a state in the United States, this is, need to attend and get their degree from an accredited program, and ABET serves that role in the United States. And basically exists for good reasons. It ensures that graduates have met the educational requirements necessary to enter the profession. And it's part of licensure, as I mentioned. But there's some bad things about it, some cons. Let's see, I wanted to mention them here. The cons of accreditation is that they contribute to the rigidity of our program. The ABET accreditation process is a frustrating process in the department, where you go through and you are looking at the details of what you're teaching, and these rules about how the ABET accreditation is applied become a template, and it drives so much uniformity across the profession. Most universities offer courses that almost look exactly the same in structural engineering. There are benefits of that, but there's also this idea that it tends to resist the innovation and the flexibility. I am among the people who say accreditation really has kind of, I don't know, run its course. This is a monster issue that you can't just sweep it away. But I think we want to be very cautious about how accreditation can lock down our creativity in education. And that's one of the things that comes even down to new topics, creating new courses, changing things in existing courses becomes seen as more difficult because we need to follow the rule, follow the template, do it just like every other university across the nation. But fortunately, in the case of that we're talking about today, professional organizations have really taken a lead. I think we've seen this topic of non-metallic building materials led more strongly by industry than by educators. That's actually not a great thing to say. I mean, educators just should be, they're the ones involved in research. They should be anxious to help new technologies become more mature. And certainly they are the gatekeepers to what the students are being taught. So educators are an important partner because they help prepare that next generation of designers. And we need to find champions within the academic community who will modify structural engineering courses to embrace the possibility of new materials. One of the most important organizations is ACMA, the American Composites Manufacturers Association. I want to give a shout out to John Bussell, who is a friend and a good source of knowledge. He's a brilliant guy working over there on that side, and helped me with some resources even along the way the last few years. And they have been working on advocacy and strategic communications and education and technical expertise and standards development. Now, in the case of the building code, there was a recognition that ACI for reinforced concrete was the proper home for a new building code like that. And so that's where we see it coming out of ACI. But there are other kind of metallic, non-metallic structural shapes. These are not reinforced concrete items here. This is more like structural steel. And these composite pipes and connections and so forth have their own challenges and their own set of adoption issues into structural engineering codes. Of course, I want to mention ACI. ACI has an offshoot organization called the Strategic Development Council, and they have been for some years holding these SDC technology forums that have featured presentations on GFRP rebars and other kind of non-metallics materials. This particular slide that I show here, presented by my good friend Doug Gremmel, who has also been a good partner for me over the recent years to bring me up to speed on non-metallics. So the one though that is important today is NEx. So a couple of years ago, ACI invented this new idea of a center of excellence, of bringing up industry to help support focused sponsorship of activities in a certain area related to concrete, reinforced concrete, and that led us to NEX. And that is focusing on code development, partnerships in industry, research projects of all sorts. And so Jersey and Aparna are part of that, and they're doing a great job getting us going. Actually, I should put an exclamation point on that remark. So in preparing for a talk like this, what do? You go to the resources that are available. And I have been looking through the website of NEX and through ACMA and other organizations that have done work on nonmetallics. And there's an amazing amount of material out there now. And especially now with the new code for design, these we're ready to see a big push forward in the kind of teaching materials and curriculum that is necessary to advance this field. So the main one accomplishment that everyone is excited about is this new code 440.11.12, building code requirements for structural concrete reinforced with glass fiber reinforced polymer. But there's going to be more. This is just one. There are other codes that need to come. But the main achievement, it's been referenced by the ICC and adopted by reference into the IBC. This is very similar to how ACI 318 code is referenced, and this is a great step forward. And you see on the screen a listing of the chapters. So I have what it looks like there's 27 chapters listed. And as you go down through them, well, that does kind of look like 318. It does have somewhat the same kind of a sense of how the mechanics are treated first, and there's the treatment of loads, and then you have elements like one-way slabs, two-way slabs, beams and columns and walls, all treated separately. And so these this logic to what 440 is should be a very smooth transition into a world that was dominated by 318. That is very important. Why? Because the 318 audience, the world of structural engineering with reinforced concrete, needs to be the champion of bringing in the possibility of using new materials. An existing engineer who proficient in reinforced concrete with 318 should feel quite comfortable considering how these other reinforcing bars might be used. And then that's just for the reinforced concrete conventional thing. But there's other kind of non-metallics that will be coming along where we have these extruded shapes and so forth as part of the load carrying system. Those things will come too. But I'm especially thinking about where GFRP bars are substituted for steel bars. So there is a couple really good things that I wanted to point your attention to. Major differences between the ACI code and 318. This is based on a nice paper by Vicki Brown, Will Gold, Carol Shield. Those three, by the way, big stars, big kudos to those three who are members of Committee 440. And they put out these papers. This particular one is a nice summary one. But basically, it's identifying that the things that are different about GFRP does influence how code gets written. So for example, just read through a couple of these with me. The GFRP has higher tensile strength, but lower stiffness. So that's going to have an implication for moment redistribution, all right? And so we maybe have some of our coefficients in the code will be changed as a result of that. In normal code design, we often are being controlled, design is controlled by strength issues, but not so in GFRP kind of situations, because deflections and crack control are going to usually control the design. There's a remark about GFRP is less effective than steel for controlling creep, the bond issues of having a matrix with that has a lower moduli than is seen in the reinforced concrete alternative. There's also a question about crack widths that can be relaxed somewhat because corrosion is not the issue. That's why we have rules about maximum crack widths, because we're concerned about corrosive salts coming into the reinforcing level. So, and there's a few more things here. Durability is definitely different, and serviceability, and then fire resistance. So we know that these materials with a polymeric matrix around the non-metallic, in some cases, if they're exposed to fire, it's an important limitation, and we need to rule out the possibility they're used in fire, where fire may be expected. A different paper by the same authors looked at lessons from case studies. I just picked out two things as an example here. They redid a design of a mid-rise building, now with GFRP. And two of the kind of practical implications are shown here. They found that in general that the GFRP RC members will have a larger cross section. Well, that's good to know. That'll ripple through the design in many ways. They found that closer spacing of the reinforcement in slabs is likely to be required due to control of cracking. Okay, so these kind of issues. It is not correct to think of the use of GFRP bars as just a remove and replace. That we take a steel design, we just take out all the steel bars, put in all the GFRP bars, and we've got a workable solution. No, it's not quite that easy. And you want to go to a new code that is specifically addresses some of these changes in properties that affect the end product. I want to now mention how important research is. Research is important for several reasons. Well, lots of reasons, but the two that I want to point to is that there's always a need in a new emerging area to keep plugging away and finding answers to unsolved parts of the problem. But a second part that I want to emphasize is these are your champions. The academic research community that is involved in research are the same ones that are going to write your textbook, start courses, create a new generation of structural engineers that think about reinforcement a little more generically. Like I have different choices for reinforcement. It's not always steel. If you go right now, I've picked out one of these just to sort of show as a visual aid. So this is one of my handy textbooks on reinforced concrete. It doesn't mention anything but steel. I guess, of course it would not. That we've never used non-metallic reinforcement. And so you have all these charts and so forth that are going to be part of the 440 code and part of the teaching of reinforced concrete in the future. And these books need to be updated. And they need to be updated. They won't get updated unless the authors are champions, feel that it's a legitimate advance for the profession, and that our students need to be aware of it. They will include it in the next version. And as soon as a few of them start, then it will become sort of expected. Who wants to be the textbook that doesn't have reference to the latest and greatest ideas? Okay, so that leads me to a roadmap for higher education. As I'm thinking about how things get into the civil engineering curriculum, I made these arrows to kind of develop a set of requirements. First, anything we deal with has to be sound basic science. I guess that just goes without saying. But there's more. We don't just put every idea that has sound basic science into the civil engineering curriculum. There has to be compelling need for these ideas, practical need in the profession. And part of that is commercial viability. If there's not commercial viability, well, then there's nobody doing the pulling that we want this. And right now, that part of my diagram here is terrific because our industry is stepping up to articulate these needs and is trying to drive it, trying to fund it. NEx, for example, NEx is funded by industry. And so what you see here is that corporations feel that they want to help get changes to the technology, what's approved, what's in code, what's taught, and they can do that by infusing resources into higher education through organizations like NEX. The next green arrows are the ones that I think still are in process. Acceptance by the profession. Right now, you can go out and find design engineers who are quite comfortable and quite familiar with using non-metallic reinforcement. But you can find a lot of people who have never used it. Certainly, and they have good reason not to know that much about it. They weren't taught it. And so that leads me to the fifth arrow, development of the body of knowledge. That language, body of knowledge, is the same language used by ASCE for accreditation. We need to understand what is it that constitutes this discipline? What is it that when we think of structural engineering, this idea about what is reinforcing, our understanding about reinforced concrete needs to now be changed so that we have the alternative materials embedded in our definition. That a structural engineer must be knowledgeable about the alternatives to steel in reinforcement. And that will allow you to move it into the curriculum and have it readily available for the next generation of professionals. I have, how do we find room? Okay, so this is always a problem. Oh man, we're gonna add a course in civil engineering. How can we possibly? We don't have any room. If I go back in the history to the late 1800s to see how they were teaching civil engineering, they all had these courses on sanitary engineering and surveying. Lots of surveying. You know what, Illinois, in civil engineering, we don't even teach surveying anymore. It's thought of as something for the professional land surveyors, but in civil engineering, it's not maybe the wisest thing, but we don't have it as a required part of the civil engineering curriculum. So we found things to shed over time. We're now more focused than we were in 1900 about what civil engineering, it means this narrowing of what we teach, narrowing. And so when we think of adding yet one more topic like non-metallic building materials, it just blows our mind. How are we going to get this done? So option one, a full semester design course. Good luck. That's my basic response to that. Masonry and wood already have shown that that's a tough call. And I really want to lead us toward option two here. I think what we need to do is redefine what reinforced concrete and what structural steel design is about by integrating alternative non-metallic materials without changing the courses as a unit. The same students need to sit in that chair and sit and learn about the materials used as more generic, as a set of properties. After all, they're all built on the same mechanics. All of our design is, linear elasticity and so forth. And so it doesn't matter what the modulus of elasticity is, just that we know it and we can test it and prove it. And then we can proceed with the design of effective structure. So I think option two is a viable option. It's seen as a win-win, meaning that the professors who are teaching reinforced concrete will most often think it's advantageous to pick up a new topic in their field. Okay, I've never seen it before. I didn't hear about non-metallics as a student myself, but I want my course to be leading edge, and therefore I will write my next version of the textbook with those kind of provisions. So the partners with authors of traditional textbook materials, very important. Now, last option, option three. Option three is a little bit where we are right now. There are other ways to reach the profession: workshops, seminars, conferences. To some degree, it's being treated today as a niche topic that appeals to students and professionals. We still are, to some degree, building critical mass of industry demand. So option three is important, no question, but option two is where the game is going to be won. We need to be a legitimate player in how we do structural design. Okay, So this just makes the same points. Entry points for new topics, reinforced concrete 1, steel structures 1, and so forth. Just a few ideas about comparing. Imagine projects where you ask students to see a standard beam, but then redesign it with another material for reinforcement, comparing the costs and performances. In the case of steel structure, imagine a case where we have to redesign the connection issues because we're using non-metallics with different kind of protocols and limitations or constraints about how we do connections. These things need to be addressed, and we are just barely getting started. I think we're going to see big progress in the next few years. Okay, so that leads me to the end. Thank you all for your attention. I am ready to take questions if there are any.
Hi, David. Thank you so much for delivering an outstanding presentation. And yeah, we will go towards our question answer session. So our first question is, so where do you see the role of new engineers or the graduates in adopting new innovations, including non-metallic materials?
Well, I think that the students are essential. Okay, I think this was about where are we going to see a breakthrough. I think right now that the best and fastest breakthrough are going to be graduate level courses. So if you're attending a master's degree program as a structural engineer, I think you should expect to see this topic. This is leading edge topic. It's a lot of research going on. If you're not getting this from your program is not up to date. So that is a strong impetus to lean on the faculty doing master's level structural engineering to consider how to adopt these kind of new technologies in their program. That's probably the first and most compelling idea we should embrace. That should be the way we do that. Undergraduates will follow in time, but right now it maybe is as a graduate level topic.
So yeah, so following to this question, there is another question which says on slide 33, it says we should select from among the full set of material choices. So what do you think that most non-metallic materials are relatively new? So where do we find the needed information, and how do we start to update?
Well, okay, that's very good. So having the framework of a code gives you a good starting point. And now you can start considering the competing detailed products that are possibly out there. And there are different products. The GFRP bars tend to get a lot of mentions, but there's other kind of rebar made with basalt fibers or, I don't know, carbon fibers. So there's actually a considerable selection of things that should be considered. Makes it actually more fun. As a structural engineer, this makes it a little more creative, a little more fun. And we don't really have that much leeway in thinking about reinforced concrete with steel bars. They're kind of standard. And in fact, they're in tables that we use and so forth. Maybe sometimes we use high strength steel bars, but now opening it up to saying, hey, we could have 10 different choices to consider. What does our project need? What could we do? That's a great set of alternatives. And that's what, so I do think that the industry is going to do that. ACMA is certainly in busy trying to make these materials available. And anyway, so the industry, this is part of the marketplace.
But also, like, there is another question which targets the thing, like, how long do you think it takes to have full credentials of non-metallic material in university courses?
I don't know. How long do you think? I personally think I'm encouraged by the momentum that is being shown right now. I think we'll see. Well, some universities already have. They do address some of these new technologies, and And so I think over, say, a 10-year window, we'll see many of the leading universities will get onto this bandwagon right away. And I think the half of the civil engineering will be laggards. There's a
Okay.
lot of schools that are not equipped
Mm-hmm.
to be adopting this. Their faculty are perhaps a little bit overwhelmed by current duties that they don't want to take on a new subject area.
Yeah.
But I think the good universities, that leading it universities, will take this on as a way to differentiate themselves from the many others.
Mm-hmm.
We are ready to take these things on. We are teaching our kids the latest and greatest. So this is a hallmark of our program, that we adopt what we see as the new technology. I'd like to think of it that way. So we'll hold it out as a get a gold star if you can include these things in your program.
Yeah. I think I
It's
agree with
really,
it.
I'll tell you what, it's up to the individual faculty to do it. That's why this idea of champion faculty should be maybe part of a very explicit strategy that even NEx could help develop this, of that a
Yeah.
list of champion.
Yeah, I think Next have a few projects in line, because advocacy is also a major focus for Next. So yeah, we do have some projects which are to advocate engineers or new graduates, and we have also been organizing workshops, and one of this is the webinar. So yeah, definitely, I think I agree with you. We have to start and then build
Yeah.
upon on it. Yeah. So our last question I would like to take is, do you think the role of new materials impact on environmental and life cycle cost with enforced adoption? Where do you see non-metallic materials impact on cost and carbon emissions?
Um, the first of all, is the topic important? Yes. Am I authoritative on to make remarks about it right now? Not really. I have not really done my homework on all the competitive issues with regard to, say, um, how the green criteria is affecting these areas. I think I'm confident that the winning characteristic of the day for structures is durability. I'm not sure I care about carbon credits very much. I don't really care about um, um, the arguments about how the materials are manufactured, because in the kind of the presentations I've seen, what wins the day is, can you make a building last 50 years, 70 years? If you can get long life with little repair, you win.
Hmm.
End of story. I don't care quite how you make it. So you can. I want longevity. I want long life cycle, and the non-metallic building materials are a way to do that. That's part of their calling card. We don't corrode. We'll be there. I mean, the materials are non-corrosive, and so they'll have long life. So I think that's one of the advantages of this new technology.
I think, yeah. Thank you, David. Thank you so much for answering all the questions. This ends our question answer session.
All right, very good.
Yeah, thank you, David. So going again to our next slide, it's once again, thank you all for joining us, and we appreciate your participation and engagement, and we look forward to seeing you in our incoming webinars. So please visit our aciuniversity.com to see the topic for our upcoming live webinars. One last announcement I would like to make is, next is funding research projects and standard and guideline technical advocacy projects. We have released and request for proposal on our website. So please do visit nonmetallic.org. If you go on next projects, and you can see request for proposals. 13 topics have been listed. We are accepting proposals until September 5th. For any details, you can click on the title to get more details and guideline of the project. If you have any questions, please reach out to us. Thank you so much again.